Okay, guys, real quick, let's go through question 1, 2, and 3. Starts on 50, goes on page 51. I highlighted the givens for you, and I put a green highlighter for the unknown. Here we have a runner. They have an initial velocity of 0. It takes them a time of 8.5 seconds and an acceleration of 1.1 seconds. So that's really my given, is that initial velocity as 0 meters per second. The time is 8.5 seconds, and the acceleration is 1.1 meters per second squared. My unknown here is the displacement, because it says what's the distance the runner could cover. I'm just going to call that delta x. So we're going to choose an equation. It has to have v initial, it has to have acceleration, it has to have time, and it has to have displacement. So if I look at the one equation that fits the bill, it looks like this. It says delta x is equal to initial velocity times time plus 1/2 of acceleration times time squared. And I'll show you a fun little coinkydink that happens from that. So if I substitute here on the left, I go delta x is going to be equal to 0 meters per second times 8.5 seconds plus 1/2 times 1.1 meters per second squared times 8.5 seconds squared. Here's the fun thing. The whole first half of that just gets deleted into oblivion because there's a 0 because the initial velocity is 0. So delta x is going to be 1/2 of 1.1 meters per second squared times 8.5 seconds squared. You square the actual magnitude and you square the unit too. So that's going to help us when we're doing our final unit analysis. The delta x, when you boil it down and punch in your calculator, was 39.74 about. If you want to do sig figs, yeah, of course you want to do sig figs. I've got 2 sig figs. So I guess you could have said like 40 point, or you could have said, like in scientific notation, 4.0 times 10 to the first. Both of those answers are in meters, okay? Distance is in meters, and that sums up that one, okay? Rolling up here, I already highlighted the givens, and I just wanted you to note that since it says deceleration, we have to be careful. At the end, we'll look at the signs of these and see if we've got that correctly. We've got a displacement. We've got a delta x of 180 meters. We'll look for that later. It does say to the south. We've got an acceleration in the negative direction. It's negative 6.25 meters per second squared. We've got an initial velocity of we don't know, but we have a final velocity because it comes to a stop of 0 meters per second. Okay, our unknown then is our initial velocity. Our equation, there's one equation that has final velocity, initial velocity, acceleration, and displacement all in it, and it looks like this. It's final velocity squared is equal to initial velocity squared plus 2 times the acceleration times the displacement. And all I'm doing is I'm looking at 4 variables. One of them is unknown. And which one of these equations has the 4 variables that I need? I'm going to give myself a little more room here. Sorry, guys. Just bouncing that out here. If I want to find initial velocity squared. That's going to be equal to final velocity squared minus 2 times the acceleration times the change in distance or displacement. Okay, so it looks very similar to this equation, but I flip-flopped these variables so I could have initial velocity on the outside. Okay, so what does that look like? Initial velocity squared is equal to my final velocity of 0 meters per second squared minus 2 times negative acceleration there, 6.25 meters per second squared. Running out of room. Don't run out of room. Don't be like me and write too large. Times my displacement of 180. I need to get rid of that square though. So I'm going to take the square root. So I can do this all in the calculator at once, or I can get the information and then take the square root. Like if I get the information, it was 2,250 meters squared over second squared. Get the square root of all that. What's going to happen is that's no longer going to be squared. That's no longer going to be squared. That's no longer going to be squared, right? So it's just going to be meters per second, which is good because we're looking for an initial velocity. So an initial velocity in the end is 47.43. Oops, 0.43 meters per second. And that's about 47 with our sig figs. Alright, so this may have tripped some of us up. That was my deceleration. If you have questions in class, we'll talk about it tomorrow. Let's look at Q3. We're given an altitude or a displacement of 650 meters. We're given from rest, which is our initial velocity, and we got time of 7.2 seconds. These are going in the up and down, so you could use delta y. If you just wrote delta d, I'll know what you're talking about here. So displacement in the y is 650 meters. That's going up, so it's positive. The time was 7.2 seconds. And the implied here velocity, that's initial, is 0 meters per second. Okay, those are my three sort of givens, and I need one unknown, so I got 4 variables total. That's acceleration we don't know. And I think if we can say what's the rocket's final velocity, or we need to know the rocket's velocity at that single point. So what constant acceleration? Let's do that first. And then let's look for final velocity. So something that contains displacement is the change in y is equal to the initial velocity times time plus 1/2 the acceleration times the time squared. So remember, we're looking for acceleration here. I'm just going to put that equation up in here too. We need to write that the displacement is going to be 1/2 the acceleration times the time squared. Why? Because my initial velocity is 0. So I can chop half of that equation off like I did in the first problem. Alright, so all that can be chopped right off. Its initial velocity is 0. Something's happening with the recording. I don't know what's going on. Stay with me. My delta y is 1/2 times acceleration. I'm gonna pause. All right, I started to rewrite the equation. I'm not quite Hollywood yet. So rearranging it, sheesh. My acceleration is going to be 2 times, instead of 1/2, it's 2 times the displacement, divided by the time squared. All right, so now I'm going to plug those values in for acceleration. It's going to be 2 times 6.5 divided by 7.2 squared. Don't forget to square. And my acceleration is 25.08 meters per second squared. That's going to round to about 25 meters per second squared. It's positive or upward. I want to make sure I have enough room for part 2. There's not a lot to it, because at this point, you know, I've got the delta y, I've got the a, I've got the time, I've got initial velocity, and I've got final velocity. I think the simplest way to find the final velocity would just say final velocity is equal to initial velocity plus the acceleration times the time, and we'll use the final velocity in here. Okay, so using the acceleration that we just found, we'll just substitute that in. So we don't know final velocity. We do know initial velocity. We took off from rest. Was 0 meters per second. And we know the acceleration that we calculated. So our answers might vary. You could use 25. You could use, 25.08 times the time, 7.2 seconds. So I'm basically punching this into a calculator. 25.08 times 7.2 gave me a final velocity of 180.576. 2 sig figs here. Let's just say 180 meters per second. Right now I can stop it.